conformal field.
Thank you. Nice to be back here. Thanks for inviting me. I'll be talking about anomalous dimensions in epsilon expansion of the Gross-Neveu conformal field theory. This is based on some recent work which was done with Rychkov, who is a postdoc at ICTS, and Ghosh and Kashi Jasmine, who are graduate students at ICTS. Let me begin. So the epsilon expansion is a well-known method to perturbatively compute anomalous dimensions in various quantum field theories in a power series in parameter epsilon, which is defined as follows. So you work in space-time dimensions, which is an integer number plus or minus some small parameter epsilon. And then the idea is to, as usual, do diagrammatic perturbation theory to compute using Feynman diagrams various observables in a power series in epsilon. So this really began with Wilson and Fisher's work, the well-known work in which the Wilson-Fisher fixed point was discussed in 1972. And so the last 4 decades or so, there's huge literature on the whole industry, computations in epsilon expansion, statistical mechanics, and quantum field theory settings. So in particular, in this work for 5-4 theory in 4 minus epsilon dimensions, the anomalous dimensions of various operators were discussed, and so what we will be discussing here in this talk will be the epsilon expansion in conjunction with conformal symmetry. So if you have conformal symmetry in a quantum field theory, as you also know, there are various it has various additional properties which sometimes gives you some additional features because they are not present. And of course, you can take the approach that you just use epsilon expansion as always, and you do conformal perturbation theory, which would be the same method, again applied to a conformal field theory. But Rychkov and Tan last year in a paper, they elaborated on a method which gives you the epsilon expansion for the anomalous dimensions in conformal field theory, which doesn't rely on Feynman diagram-based techniques. So you just use conformal symmetry, and it will give you, at least it will give you the leading order anomalous dimensions. So the focus here is really much more on the method rather than the results. The results, they will be, of course, there will be some new results. You can always get them if you want using Feynman diagrams. In some cases, at least, that will be much more cumbersome. So this is interesting because it gives you a way of computing observables using the power of conformal symmetry.
So we got some new results as well.
So what they did was that they computed. They actually didn't, because they computed the leading order anomalous dimensions for a class of composite operators in the Bosonian two-line vector model. These were essentially, so for the lower operators, so if you consider operators like phi to the power n, so this was more or less known, the leading order anomalous dimensions. We'll do similar thing for fermionic theory. Here it turns out that the results for the low-lying operators are known, but for higher composite operators, they were actually, as far as we know, they're not known in the literature. And unlike the use of Feynman diagrams, here dealing with higher composite operators is not more difficult because the method is such that it just works for them also. And so I'll elaborate on that.
And this fact that you don't need to use exclusively Feynman diagrams has to do with conformal symmetry?
This has to do with conformal symmetry, though I must stress the fact that, I mean, the places where this method works, so you will be dealing with interacting fixed points which are however perturbative, so they are connected to free CFTs. And therefore, any place where you can use this method, you can always use Feynman diagram techniques also. So there's a limitation of this feature. You can't deal with isolated fixed points to compute in this way. but nevertheless, this is the first time that the epsilon expansion has been developed systematically without recourse to dichromatic techniques. And of course, the state of the art here is it's really quite a well-developed subject. So people have computed to order epsilon 5 the anomalous dimensions of various operators. The simplest operators in the field. Okay, so some general remarks about the Gross-Neveu model. So this is a renormalizable quantum field theory in 2 dimensions. It consists of self-interacting fermions with a UNF global symmetry. It has a discrete chiral symmetry which is spontaneously broken. So Gross-Neveu developed this model basically as a toy model for QCD because it exhibits some interesting dynamical features which are also there in QCD, in particular asymptotically free. You have chiral symmetry breaking and various other things. So we will study it in 2 plus epsilon dimensions. We will be dealing with these fermions. So I is the isospin index, the UNF index. Alpha is the spinor index, and you have NF copies of these fermions. And this is the usual standard action for the theory. There is this quartic, the usual 4 Fermi coupling. And so this is marginal in 2 dimensions. So we'll study it in 2 plus epsilon dimensions. And there you have it turns out if you study it in 2 plus epsilon dimensions, then you compute the beta function perturbatively in the coupling. Then there's a weakly coupled UV fixed point. Which occurs at this value. G equal to G star is a moderate value quantity. Okay, so at this point you have a conformal field theory, which is weakly coupled. And so this has been well studied, and using usual Feynman diagram techniques, people have computed perturbatively the anomalous dimensions for the fermion. So this is the total scaling dimension. This has a part which is the classical canonical scaling dimension, plus the quantum correction. And similarly for the fermion bilinear. And so the state of the art here, I think, is like order epsilon cube or something. But anyway, I'll just quote the leading order results. So the fermion gets the correction to the leading orders of order epsilon square, and the fermion bilinear has this. So this is what is known. So we will reproduce these results and also results for a whole class of composite primary operators. So I will elaborate more in a while, but these will be operators which would, in a free case, they would look like fermion bilinear to some power. And so for p equal to 1, for example, the result is known. And the calculation is similar in spirit to what Rychkov and Tan did in similar computations in the scalar case. But here there are some new features which arise because you're dealing with fermions and point them out as we go along. So as I already alluded to, so you don't use Feynman diagrams for computing this. We'll use conformal symmetry, and so mainly just 2 and 3 point functions in the theory and the operator product expansion. So at this point, let me just mention that, of course, conformal symmetry, there's much more to it. If you use the full power of the OP, then you also have OP associativity and bootstrap and all that. And all that is relevant here. However, the leading order in the epsilon expansion results don't actually require that. So I'll talk a bit more about it. So here we'll just use some very, very basic CFT inputs. And other than this, we'll use that will be an essential feature, is the multiplicity combination which occurs in interacting conformal field theories. So let me just state the assumptions and set up the notation.
So here, whenever you say leading, you mean leading in epsilon?
In epsilon.
And how about 1 over n?
No. So these results are not large n. These results are.
Those are exact. Those experiments are exact.
Yes. So these don't require large n. Okay. So the assumptions are the following. So you work with. Sorry.
Yeah. What you're going to use the epsilon expansion to? Are you going to use the expansion to say something or say what happens with Anomalous dimension other dimensions? And what is the interpretation of this epsilon expansion?
No. So the epsilon expansion. So for example, the fact that you have a fixed point at. So when G star is when the coupling is order epsilon, you have a fixed point. So you can do the expansion in the coupling. So given any observable, you write the loop expansion, right? And the epsilon expansion gives you an alternative way of doing it. To match them to leading order is straightforward because, for example, if an observable is given to leading order in epsilon, right, then you can use this relation, the last relation here, to find the leading order one loop correction in the coupling. So you can match it to physical results. When you do it to higher and higher orders, there are more subtleties. You can still do it, but there are things you have to worry about the normalization scheme and so on. But you can still do it. So this is a formal method, of course. In the end, you want results in integer number of dimensions. But this way, you can do the computations, and then you can match them, say, with the loop expansion to
Loop expansion, you will try to match it into expansion in 2 dimensions.
In 2 dimensions, yes.
So, you will say you will be able to invert this relation to write epsilon in terms of G star?
Yeah, so higher, this I'm not sure if, so for example, in the ON vector model in 4 minus epsilon dimensions, it turns out that there, so what Wilson and Fisher found was that, you can take epsilon equal to 1, which, is not probably small, but it turns out that you still get the correct results. So when epsilon equal to 1, 4 minus epsilon is 3, and that's how you get the Wilson-Fisher fixed point at this point.
There were some 1 over 4 pi.
Yeah. It is basically because you're not doing the expansion in epsilon, but epsilon over 4 pi or something. So that is why that works. I'm not sure if in this case the fixed point I think has been studied numerically and it exists up to 4 dimensions here. I think numerical studies tend to that. It's the case also in this case. But this way will give you the leading order quantum corrections for the endless dimensions of various observations.
So you only do it in higher order, I should be able to invert this relation between epsilon and G star, is it?
Well, higher orders, I think you have to worry about, the renormalization of operators, and in fact there are more subtleties which I have a slide at the end about that. Actually, when you go to higher orders, actually beyond order epsilon square, it's actually not consistent to deal with just this action. There is a whole tower of terms you need to add, which is a technical aside, so let me just talk about it in the end. But doing it to leading order is, everything is okay. So, alright. So you make the assumption that, you have, so the point really is that you have a free CFT, and then there is an interacting CFT, which is some deformation of this, and it's smoothly connected. So for every primary operator, let's say some operator O in the free theory, there is a counterpart, which we call this V subscript O. And as epsilon goes to 0, so your coupling goes to 0, you get the free limit. This operator goes over smoothly to O, in the sense that correlation functions involving these operators go smoothly to the free correlators, and that's epsilon going to 0 limit. So there is an assumption. Then there's a usual standard assumption about the epsilon expansion being analytic in epsilon and at least being critically convergent and so on. So all those standard assumptions are still there. So we'll assume we'll expand this series in epsilon. So we will be dealing with the first order result only.
So
the leading quantum correction.
Anomalous connection you want to expand in terms of some epsilon.
Epsilon, yeah. And as I already mentioned, so this works for perturbative fixed points. So you have an interacting conformal field theory where the fixed point occurs at something which is order epsilon. And then you get the free controllable field theory that's selling to the zero limit. So the other key feature which we'll use is something which is well known from the study, especially of supersymmetric field theory, which is the phenomena of multiple shortcuts. So there it happens that once you are in, when you turn on some couplings, you have some primaries in your field theory. The multiplets, different multiplets combine to form a single multiplet, and this is a general feature which will actually exploit to do calculation. So basically, the point is that there are in the field theory you have primary operators, say O and O prime, and the corresponding operators in the interacting theory. So this is an equation which, for example, from the Lagrangian point of view, this is just the equation of motion of some operator, where alpha is some small coupling constant. So now this equation is telling you that this operator, V of O prime, is a descendant because it's P acting some other operator. So even though in the field theory you have two primary operators, in the interacting theory the multiplets have joined in some sense, and this operator V of prime is no longer a primary operator. So within the conformal multiplet is V of O. So yeah, let me make some general schematic remarks about the method that we use. So for any theory where this kind of methods are applicable, this would be more or less the approach you will use. So the point really is that you choose operators in the field theory. You choose operators. So these are certain composite operators, OP and OP prime. Okay, this is very schematic. I'll just illustrate everything in the Gross-Neveu model, but just to give you a sense of where we're heading. So O and O prime are certain primary operators in the field theory, and the point is to find the OP which is sensitive to this phenomena of multiplet recombination. So it's connected. Yeah. So you find certain composite operators in the field theory such that their OP includes these operators O and O prime, which remember occur in the equations of motion, which I just showed you here, the multiplet recombination equations. So these are the equations. So this is my notation. So O will always be a free theory operator, and V of O will be the corresponding counterpart in the interacting theory. So if you look at this equation, you can use this to. So first you look at the free theory. You find a suitable OP which includes O and O prime. These are the leading primaries. So this has been written in a very schematic way. I've suppressed various powers of X and so on. And so this will be a primary O and all its descendants. Some relative coefficient rho, which is some, and you can determine combinatorially by doing the contractions. Then O prime is some other primary and all its descendants and other terms. Now when you go to the interacting case, because remember that V of O prime was a descendant now, so it sits here, right? So when you do the OP, you have the primary, which is this operator, then this is its descendant, right? And if you use the equation of motion, which is the multiplet recombination equation, that tells you that you'll get Q alpha times V O prime, right? And now if you want to, because you have made the assumption that you want to connect smoothly with the free limit, therefore it will follow that if you want matching in the epsilon going to zero limit, this coefficient here rho should be Q times alpha. Right? So it's a rather straightforward method. And now it turns out that So alpha is something which is alpha is basically the coupling. So the point of view that we will take is that we'll de-emphasize the Lagrangian approach. We'll actually determine alpha in terms of epsilon without making mention of any Lagrangian. But as I already mentioned, implicitly it's already there. So the combination equation really follows from the equation of motion. And there alpha is something which is proportional to G star, which is order epsilon. So because alpha is an order epsilon quantity, and rho is just the free theory OP, so you just determine it by doing big contractions, so it's just some number. Therefore, in the interacting OP, this subleading term, the coefficient of the subleading term, will have a singularity. So it will have, at least it will have a first order pole. And that we'll see explicitly how that happens.
So, but this equation of motion thing, the relation between VO and VO prime, through this derivative, that is supposed to be exact in epsilon, or that is also true only in leading order?
No, that is supposed to be exact. We will use it to, the renormalized operators in the interacting theory. This is just like the Schwinger-Dyson equation of motion, which, of course, so that is where it comes from. But in the CFT approach, you can just consider it as an operator relation. In the interacting theory, there are operators which in the free theory were primaries but are not descendant. But this is exact.
Well, if you want to, imagine if you want to rewrite the Schwinger-Dyson equation as an operator equation, then of course you will have to have all the counter terms, like additive counter terms and multiplication. The definition of VO and VO prime is...
Yeah, that will depend,
right?
Yeah, that is right. Yeah.
So it is some scaling field at the Wilson-Fisher fixed point. Which is appropriately defined. On that, this is true.
We don't know what exactly VO is. That is the point. We don't know. This is some. No, the only thing we really need is that it matches correctly to a free theory operator. That is right what you're saying. And it turns out that so this simple relation here. This leads to a difference equation which determines for you the leading order anomalous dimensions. So this is like the gist of the method, and I just illustrate this in the Gross-Neveu model now. Are there any questions?
Sorry, why is there a singular? So why is Q of order epsilon?
No, Q is not order epsilon. Q is a function of epsilon, and alpha is a function of epsilon. Alpha is order epsilon because, so if you derive this equation, you can just...
I think just pointing out that slide where it should be Q is order 1 on epsilon.
Sorry, Yes, right, this is right. No, this is alpha. Q is order 1 by epsilon. Sorry. Okay. So this will be the class of composite operators which we'll be dealing with. In the free theory, you can build these primary operators, composite operators, and we'll be dealing with the counterparts in the interacting theory, so this will be the notation. P2P denotes the operator, which in the free case goes over to this. Okay, and likewise there will be, so this will be some scalar operator. Likewise you will have, so I've suppressed all indices. There are the I indices, the isospin indices, and the spinel indices and stuff. And then you also have fermionic operators, which are these. Now, in this case, you have this first order equation, which tells you that the operator V3 is a descendant in the interacting theory, and will compute to leading order in epsilon the anomalous dimensions, which we'll call. So this will be the anomalous dimension of this operator, and this will be one of this operator. And so now alpha, of course, is you just write the Lagrangian, and if you determine alpha, it's just number times the coupling constant. But we don't want to take the recourse to a Lagrangian, so it turns out that you can determine it in terms of epsilon directly. So you just write a 2-point function for this operator. I hope the notation is clear. So V1, whenever you see this thing, it just means that P is 1 here. So V1 is just a fermion in the interacting theory. So you consider the 2-point function. The form is determined by conformal symmetry. You differentiate both sides.
So V1I is just psi I.
Yes, psi I. Yeah. And so you differentiate. So you act by del slash with respect to x and y on this. So you get minus alpha squared.
Is it here 1 or here 2?
No. So
T is 1. Right?
So this should be. Is it where? Yeah, this should be. Sorry, there should be 0. Yeah. So I just mean that there is a thing. Yeah. It should be equal to 0. So
What is the V's bar and Z?
it's just the conjugate. It's this thing. So you deal with psi and psi bar. So in the field theory. So these are. All right. So you differentiate both sides by acting by del slash, and now you want matching with the free theory. So in the free theory, this 2-point function. So remember, this thing in the free theory is just this quantity. So psi bar psi at x. And there is a free theory correlation function. You can just do big contractions, compute it. It will give you factor of n minus 1. So n, remember, was 2 times the number of fermion species. This is what you get. And now you just match both sides. Turns out del psi is just this quantity. So it's determined in terms of the leading order, the anomalous dimension for the operator V1. Okay, so let's go over to the OPs in the theory. So let us now consider the OP of these operators. This is the operator which is the interacting theory of the V2P. So V2P plus 1. So these OPs you can write down just on the grounds of dimensional analysis and what kind of geometric structures you can get to fix the problem. So this are the leading terms which we will need. Of course, there are more terms. I haven't written them down, but these will suffice for our purposes. So this rho here is the combinatorial coefficient. So you can determine it by doing fermionic big contractions, and this is somewhat involved combinatorial exercise which we did in this paper. So
there are more terms, meaning terms which are less and less singular in the x squared things, or
and various other operators also.
Those will all presumably be less singular in terms of 1 over x1, 1 over x squared.
Yeah. You'll have the full OP, but because we'll use the multiplicative combination which will relate these two operators. So this is all we would need at the rate of and we would need this relative coefficient between these two operators. So this you can work out. So Chetan and Palla made a paper last year in which they developed a technique for computing this in for the bosonic case, the OM vector bodies. There's some recursive way of finding. It's just a combinatorial exercise. So we worked this out, comes out to be this. Now let's look at the corresponding operator product expansion in the interacting theory. Okay, so this is the operator corresponding to this. We look at this. So now, in general, you will be able to write down these two kind of structures. So you basically write down everything you can, which is allowed on the grounds of dimensional analysis and all kinds of geometric structures which you can have. And then you can separate terms which contain even number and odd number of geometries. You can separate the two. And so these things are determined in terms of the scaling dimensions of the operators. And now the point is that...
So in the interacting theory, so you're assuming that V1I will appear on the right hand side.
So if you just look at, so this is a bosonic operator and a fermionic operator. Right? When you take the OP, you'll get all possible fermionic operators which can occur and which are not forbidden by some symmetry or something. So in general, you will get everything. So you will get V1i, and then you will get, well, V3i will be descendant of this, but again, other operators, V5 and so on, everything will occur. But again, for us, the leading order thing will suffice. Same thing. And now you can see that if you, now again you want to match this OP with this, in that cell going to zero limit. So in that case, you can see that, if you, when C acts on V1, you have two gamma matrices there. So this del slash on V1 will give you a V3. And therefore you will be left with a single gamma matrix. And that you will be able to match with this here. So, I mean, I'm not giving the details of the calculation. The point really is that the only way that this thing will match with this in that cell going to zero limit is that only this operator can be present. So if this operator is present, then it will give you gamma matrix structures which do not occur in the free case. This you can just work out by doing the computation.
Sorry, just the difference between the first term and the second term is that there's an X slash appearing in the numerator in the second term.
Yeah, so that means that this has
some additional X slash
yes, it has
inside the C.
Yes, it has one more, this structure has one more gamma matrix in all the terms that it has. And therefore, when you match this with the free theory, it turns out all these coefficients will have to be zero. Otherwise, you won't be able to match with the free theory.
The first two have to be zero. That's what you mean?
So these terms have to be zero. It's basically just that.
No, the C prime should supply one X slash.
Yeah.
From its. So therefore, the V1 prime term should be there.
Sorry, which one?
The V1 prime.
No, if the V1 prime is here, then so del slash on V1 will give you V3, right? And then you already have an X slash 1, 2 here. So that will lead to a structure which is like X slash 1, 2 times X slash 1, 2. Yeah.
Okay. Alright.
So and here you have, like, as you can see here, right? Because V3 has to go over to this operator here, right? And this thing only has a single gamma matrix. Whereas these terms, because you have an extra X slash 1, 2 here, this will give you two gamma matrices, so you can't match them.
Nice.
Yeah, nice. So in this limit. And likewise, you can consider this within like 3-point functions. So as is well known, the 3-point function is fixed on grounds of conformal symmetry. So if you have operators in arbitrary tensor representations, then for the 3-point function you get finitely many structures. In particular, if you take this 3-point function, which is one scalar and then two fermions, then it turns out there are two structures which can occur in the 3-point function, which are the following, this and this. And so we'll consider this correlator in this kinematic regime. So you take x2 to be 0 and x1 to be very small compared to x3. Okay. And now again, if you again consider the free limits and you want to match this with the free correlator, then it turns out that G1 has to be equal to 0. So this again follows from, if you just look at this OP here, right? So now you want to consider this 3-point function in the free case, right? So you add a fermion in this equation here. So you add a fermion here, take a 3-point function. And now remember, these are primaries. So the overlap of this with the additional psi would just be 0, right? Because they're different primaries. And this will give you some structure, which will be like x slash, because the 2-point function of two fermions is like x slash.
Like constant. So you're saying the C prime has to be 0.
C prime has to be 0.
And C will do the job.
C will do the job.
So let's see how it does the job. So
yeah.
E0
yeah.
will give me the first term. Just I.
Yeah.
And then there is a derivative acting on...
Yeah, these are actually similar terms. So I mean, you can, for example, del slash acting on V V1
Yeah.
will give you a V3. Right? So this will be like x/1 to V3.
Which is the second term there.
Yeah, which is second term here.
And what is V0 doing?
No, this will also be the same because this has
one gamma missing.
yeah, so it has, we'll have to put in gammas and use the equation. The equation is that del slash V1 is
So
equal to
V0 and V1 are roughly similar
Yeah,
things.
so, yeah.
Up to some gamma gamma.
Yeah,
Okay.
that is right. Yeah.
The information about epsilon is in that extra relation that is. Which order in epsilon you are. That goes in the relation of what the derivative acting on V1 gives you.
Yeah, so right now we haven't made, basically when you use that relation that I wrote down, rho equal to Q times alpha, that will enable you to extract the leading order anomalous dimension in epsilon.
So, but on the right hand side, you say you want to match it with you take the epsilon goes to 0.
Yeah, yeah.
So you must also be putting some information which order in epsilon you are expanding the right hand side.
No, this is not. This is exact. Like this is not a leading order.
Oh, this is just exact.
Yeah, this is just a 3-point function. In any conformal field theory, the 3-point function is fixed just on grounds of conformal symmetry. And if you have like 2 spinor operators, then there are 2 structures you can get, which are these. So this is exact. There is no approximation.
Yeah, but then why is the epsilon goes to 0 limit comes in the right hand side?
The epsilon going. No, so these. I mean, these things might be these coefficients can depend on the coupling, right? I mean, this will be like an OP coefficient or something, right? Which will tell you which theory you are dealing with. So those can determine epsilon.
So you're matching this with what, like this G1 and G2? You will be matching with the field theory.
So G1, as I told you, has to be 0 in this case, in this particular case.
So you are matching this with what, like
the field theory correlator.
So you are matching it up to order epsilon.
Order epsilon.
When you take the equation, like then that will have alpha squared like this terms. So those will be higher order.
Those will be higher order.
So you only consider up to V3.
Yeah. I mean, higher than V3, the terms you will get, they won't be. Yeah, they won't. To leading order, they won't affect your results. And
actually, I'm confused about this. The definition of this composite operators, B2B, etc., etc. I mean, if I demand that B2B is that composite operator, which becomes psi bar psi to the power P in the free theory, that does not uniquely define what B2B is. You know, I'm starting from some UV CFT, and I'm flowing down by some coupling. There is a whole thing about which way I define my counter terms to the operator. So this is composite operator renormalization. So there's a lot of mess in that. What is the scheme that I choose, etc. So V2B, according to you, will be something, and V2B, according to me, will be something else. Of course, if I further demand that at the Wilson-Fisher fixed point, it's a scaling field. But if the Wilson-Fisher fixed point is finitely away, there's a lot of scheme dependence.
But we are not really dealing with that case. We'll take epsilon to be a small map parameter, and we'll work with a fixed point, which is always a perturbative fixed point, which is weakly coupled, and which is so the coupling was always order epsilon.
No, but if I want a reasonably high order result in epsilon. Then the scheme.
If you want a reasonably high order result in epsilon, in this case, it turns out then you actually have to. So my last slide is actually on that, but if you want, I can go there right now. So
no, we can wait till then. I'm just asking, what is the additional piece in the definition of V2B? You said one definition is that V2B is that operator. Which, when taken to the UV CFT, becomes psi to the power P. According to me, this is not a unique definition.
So it is true. I mean, in general, if you flow from some CFT to any CFT,
or non-CFT, I'm just flowing down to something.
Of course, here we will only be comparing fixed points. So there's a free CFT and
so the additional piece in your definition is that V2B becomes a scaling operator, becomes the primary field of the IR CFT.
Yeah. In this case, it's the UV CFT, but yeah.
Now, with that definition, you say that this Schwinger-Dyson equation remains true.
Yeah.
That expression would be right. It's not here in my head.
Yeah. So I mean, there are various subtleties at higher order in epsilon. In fact, the Lagrangian that you write down with just a single four Fermi interaction that you can't deal with once you go to order epsilon cube. So I'll make this point towards the end. Yeah. And there, to be able to, for example, if you work in different renormalization schemes, suppose somebody wants to work in dimensional regularization, someone else wants to work in some other probability. Then
even in dimensional regression, if somebody wants to use some, it's like the difference between MS and MS bar and all that stuff will come.
So there you will have to actually include a whole tower of operators which are actually there, and so it's a subtlety which really shows up at higher orders in epsilon. So we have to actually.
When you say irrespective of that,
there
is always this what you call shortening equation in any which definition of these things.
Yeah.
Okay, that's not. That's not completely clear in my head, but we can discuss that.
Okay. So now. Okay, so I mentioned this OP in the free theory, and the structure C prime is 0. Now there are various coefficients A0, B0, and B1, and so it's a standard exercise to determine all these. So it's well known that in the OP, conformal symmetry basically fixes for you all the coefficients. So for each primary, you have a OP coefficient, and then all the descendants of that primary, all the relative coefficients are fixed. So you can do that just by, you take the OP, act by the special conformal generator. That will fix for you all these coefficients. There's another way, which is to match 2 and 3 point functions. So, which is so you basically do the same thing. You consider these operators. So this is a 3-point function. You know the exact form of this, just in grounds of conformal symmetry. So you write that down. And then you consider the OP of these two operators, which I wrote down in the previous slide. Here. Right? And then you insert this operator, and that will reduce it to 2-point functions. And then you can match these two sides, right? The exact correlation function that you already know, and the 3-point function computed using the OP.
No meaning in terms of the A, B, and C, which in the interacting theory I don't know yet. But I don't know it as an epsilon.
Yeah, of course. So A, B, and C are determined linear combinations of the various scaling dimensions of operators, and of course those you don't know.
Yeah,
that's what we are computing.
Right.
So in fact, that is the way you will get when you match these two. So when you compute the 3-point function in these two ways and match the results, you will get this set of relations. So remember that G2 was the, right, so this is one way of computing the correlator. And then the other way was using the OP, which has these coefficients A0, B0, and B1. And if you match them, you will get this set of equations. If you want, you can also derive them by just considering the action of special conformal generator. Because the point really is that for any primary and all its descendants in the OP, all relative coefficients are fixed by conformal symmetry. So you can find them whichever way you want to. And now, so again, you go back to the free theory OP, which I wrote down here. So this OP at the top here. And now, in the free case, when you compare these two sides, you will get these relations.
So what is the information of the anomalous dimension in this case, like in the interacting case?
Sorry,
anomalous dimensions like the gamma.
I didn't get it.
Anomalous dimensions that we're computing.
So
which of them?
No, so this fits here. So these equations I've written these will determine, so B1, the coefficient B1 here, if you solve for B1 using these equations.
Yeah, he is saying that if delta 1, delta 2p and delta 2p plus 1 are known, which is the information about the 2-point function of these operators, V1, V2p and V2p plus 1, then the OPE coefficients or the 3-point functions will be known.
Yes,
that's the state.
Yeah, so of course you don't know, I mean that's the whole point. You want to compute the anomalous. This is the total, for example, this is the total scaling dimension of the fermion, which is a classical piece, which is 1 plus epsilon by 2, and then the leading order, the anomalous dimension. Right? So that so that this has contributions from both of them. And so this gives you a relation, this thing when you match with the free thing, this gives you this relation, right? And what I've written down here, so this is just this coefficient, this is B1, and B1 is this coefficient in the OP. So remember at the start I gave you this way of how you relate Q and alpha to rho, right? So Q was this piece basically. So in this case, so B1 is Q, right? Some combination of B1 and B0 is Q. Because here, this term is sensitive to multivector combination. Because del slash on V1 will give you V3. Right? So this operator is what I was calling Q. And therefore, so this is the relation that Q times alpha is 0. Right? Where Q is just this coefficient B1 in this case, which you can determine using the OP in the 3-point function. Right? And now if you write, okay, so that's one equation. And as was pointed out, you don't know what the anomalous dimensions are. So this gives you a relation between various anomalous dimensions of various composites. Right? If you expand this, there will be a classical piece which will cancel out between these ones, and will give you a relation between anomalous dimensions. Now it turns out that just one relation doesn't suffice in this case because you have bosonic operators, composite operators, and you have fermionic operators. This is an additional feature of this case, and you'll have to do a similar analysis for another 3-point function. So if you want, this is actually the same 3-point function we were discussing earlier, but now in the limit that, say, x1 is finite, x1 is 0 and x2 is finite. Right? So that was boson, fermion. This is the other way. It's the same 3-point function in a different kinematic regime. You do the same thing here, exactly same thing. It turns out that in the OP, which I wrote down for you, which had two structures in C and C prime, in this case only C prime will contribute. And in the 3-point function, so earlier G1 was 0, this time G2 will be 0. And again, the simple reason is just for the gamma matrix structures to match. So
this slide is just the statement basically that OPE coefficients are the same as the 3-point. That's what you are using.
Yeah, that's good.
And the last slide does not give this relation between the same 3 anomalous dimensions, right? So it introduces one more extra.
What
what
is an NEP?
You are saying.
Yeah, this is true for NEP. So basically the point is, if you look at these equations, now you import the fact that, I'll show this. Right, so now these are various definitions. So if the anomalous dimension of the composite operator, it takes by P, you expand. Of course, we will only need YP1. So this will be the leading order coefficient, right? So we write this as follows. Now del 1 is the classical scaling dimension plus the anomalous dimension, and then this will be the similar thing for the composite operators, and this is what you are after actually, what this quantity is. So the for the operator, for the fermion. So I didn't actually do this, but you can from the fact that the operator V1 is related to V3, the interacting theory by this recombination equation. So del slash V1 is alpha V3. Therefore, there is an exact relation between the operator dimensions. So del of 3 is exactly equal to del of 1 plus 1. Right? And that will give you a relation between the anomalous dimensions of this operator and this operator. From that, you can figure out that for the operator psi, the leading order anomalous dimension will be this quantity. So this is something which is already known. You can also compute perturbatively. Alpha we had already determined in terms of gamma 1 at the beginning, if you recall. So when you input all these definitions in these recursion relations, right, then you will get a difference equation for these leading order.
You use leading order Feynman diagrams around the free state.
Yeah, if you compute it perturbatively, that's what you would do. Yeah. So this is a known result. So for the fermion and for the fermion bilinear, these results are known. In fact, they are known for these two operators. They are known to order epsilon cube. But for higher composites, they are not known as far as we know. But now you have a recursion relation. So you have two sets of recursion relations, which deal with. So these will be your bosonic operators, and these will be your fermionic operators. So if you had considered just one relation, then of course you won't be able to determine these. You need two relations, and now it's easy. You can just, for example, you can add the two and then subtract the two and then determine what these leading order corrections are. So that's what they are, and so you get the leading order anomalous dimension of these primary composite operators in this CFT to leading order. So let me just make an observation. So you can see that if you consider the operator, this quartic operator, which is marginal in 2 dimensions, psi bar psi whole square, then you can see here that the order epsilon pieces cancel, and therefore the leading correction occurs at order epsilon square for this particular operator, psi bar psi square equals to for p equal to 2 here. Okay. This is also true if you look at the known results for example, the ones that Rychkov and Tan computed. For the ON vector model in 4 minus epsilon dimensions, you have exactly the same thing. So here, there is to consider the operator phi to the power 4 in 4 minus epsilon dimensions. So that is marginal when epsilon is 0 in the free case. And there also, the anomalous dimension of phi to the power 4, it starts at order epsilon square. Probably has something to do with its being marginal in the free case.
Yeah, that is true. In fact, the beta function is quadratic. The beta function does not have a linear piece.
The beta function doesn't have. Yes, when epsilon is 0, that is true. When epsilon is non-zero, there was a piece which was.
No, but this calculation is done only anyway in for diffusion theory in epsilon.
Yeah.
Where up to this order I can replace epsilon by g.
Yeah, that is true.
So therefore, it is saying that the gamma it does not have a g independent coefficient. It has only gamma starts with g.
Gamma starts.
So therefore, beta should start with g square.
Yeah.
Which is the same as epsilon square to this order.
To this order, yeah. That's right.
So that proves it.
Okay.
Right. Yeah. For a marginal for an operator which is marginal at the unit CFT, beta should start with g square, not g.
Yeah.
Therefore, gamma should start with g. Gamma is just a derivative of beta.
Gamma is a derivative of beta. Yeah.
Right. Yeah. Therefore, you cannot have a constant piece in gamma, which is the same as saying that right? So
yes. Yeah. So that is one thing. The other thing is that again, if you do a large n computation, for example, then you should find that. So now for any value of p, for large n, these two p's will cancel, and you'll again have the same result. That the leading quantum correction will get order epsilon square. So these results, as far as we know, these have not been computed. I mean, in principle, I think you can do them using Feynman diagrams, but they have only been done for p equal to 1. So, okay. So let me these were the details, and let me just almost done. So let me just discuss some features of this method. There was no recourse to Feynman diagrams, as I already pointed out. There are no large N assumptions in doing all these computations. So that's a good thing. And then
so in the previous page, so these results I could have got by pre-filled Feynman diagrams after the leading order in epsilon, right? Or not?
No, this includes one loop corrections.
Yeah.
Yeah.
So the leading loop correction.
Yeah, leading. Yeah.
And now you're going to say that you can get this YPN values for higher values.
No, that's a much more involved exercise. So I'll just make remarks. So in fact, let me get there.
Okay.
So anyway, this result through elaborate Feynman diagram computations, people have computed for low values of the leading order correction. In general, as far as you know, it's not known. But now, so one feature is that in this case, these higher composite operators are simple to deal with. If you do Feynman diagrams and you have, as you increase the number of fields, of course the complexity increases. Maybe at large N you can do it easily, but we're working at finite N. So these are some positive features, and there are various limitations, of course, which should be pointed out. One I already alluded to is that isolated 6 points you can't deal with. So really, the kind of CFT that you're working with are always the ones where, in principle, you can do Feynman diagram computations and compute those things, maybe with a bit more effort. That's one thing. The other is that the particular method that I showed you enables you to extract only the leading order anomalous dimensions. There's been some recent work by Amin Nizami and others in ICTS in which they use this Polyakov. So this is actually the classic paper which is the first CFT bootstrap paper on Hamiltonian approach to conformal quantum field theory. So there the Polyakov discusses basically two representations of looking at CFT 4-point functions. One is what he calls the unitarity approach. So you look at the 4-point function in momentum space, then you do a certain analysis which gives you gives you certain terms which occur with log in momenta or something, some logarithmic terms, and then you use the operator algebra to do the same computation in which those terms are missing. And so for consistency, you require those coefficients vanish. So anyway, so this method was used by Amin Nizami to actually determine for the ON vector model for one of epsilon dimensions. So the low-lying operators, they could again use CFT techniques to determine to order epsilon square the anomalous dimensions of various operators. And it is to be expected that at that level, once you go beyond order epsilon, you will need to use the conformal bootstrap, one way or the other. It's also an interesting open problem to see if, so for example, Polyakov had to assume that, and these people also, they assume that the exchanges between, the kind of exchanges you include in a 4-point function, then it's okay to deal with just a certain scalar and isospin 2 exchanges. And it turns out it works there. And it might be true that if you want to, okay, this is just speculation, but it might be true that if you want to work at, say you want to compute the anomalous dimension to epsilon to the power s, some fixed order, then it might be the case that you have to consider 4-point functions in which the operators being exchanged are only up to order s spins. Of course, there's no proof of that, but that might be the case. So there's very little work actually done on extending this beyond order epsilon. This is the one work which does it in one particular case. There is one more thing, which is there are technical assumptions also here. So the work that we did, and also, for example, this work. This relies on this assumption that the anomalous dimension of the lowest operator, which is just the fermion, it starts at order epsilon square. So this you can already see if you look at this equation here. Then it turns out that you require that. Write that equation down. But yeah, I mean, if you take gamma 1 to start already at order epsilon, then you won't actually be able to solve these equations. And you just find it out if you work with them. And so that's one assumption. The other assumption is the possibility of being able to find OPs which are sensitive to multiplet combination. So, we were able to choose OPs in which, the free theory OPs, in which the leading order terms were operators, which, in the interacting case, they came and sat in the same conformal multiplet. Now, this might not generically happen in every CFT. So one might wonder about what kind of CFTs you can do this in. For example, the Gross-Neveu CFT, you can study 4 minus epsilon dimensions. So there, in fact, it seems that a straightforward extension of this approach would not work because the fermion, if you look at the fermion equation of motion, then the terms that appear there, you're not able to find an OP which includes them both. In 3 dimensions, 3 plus epsilon dimensions, you might be able to do it. The other thing is QED. So QED, if you work in dimensions between 2 and 4, then QED also is a 6 point. And Zavarkomatowski and collaborators, last year they have some papers in which they computed again the leading order anomalous dimensions of, I think, psi bar psi square using Feynman diagrams in conformal QED. And it might be the case that you can use it, these techniques there. So you will have to find multiplet combination equations of certain gauge invariant operators. And if you can find OPs which are sensitive to these, then you can use multiplet combination to actually determine the anomalous dimensions. And various abelian Higgs models and so on. So
in your case, gamma psi equal to order epsilon square is not an assumption; it follows. In a way, you have proved it by using your shortening, consistency with the the multiplet recombination or whatever.
No, so actually to be able to write down this equation, I didn't actually to be able to write down these recursion relations. Yeah. So remember, so y1, 2. Okay, so maybe somewhat cluttered location, but.
I'm saying, suppose you say that the gamma of psi started with epsilon. Then these equations will simply not be solved.
No, you won't be able to solve them. So the fact that you write y12 to be certain non-zero quantity and y11 has been assumed 0. The reason is that if you don't do that, you won't be able to.
Oh, things will remain undetermined. That's what you mean.
Yeah.
Okay. Yes.
So you have to assume that. Yeah. So basically, this equation
starts from ICTS.
Yeah. So if you look at this recursion relation here, let's say this one, and if you put in, so you write this as a classical piece plus an anomalous dimension piece, then that gives you this relation. It's basically the fact that alpha is square root of gamma 1. If you recall, you determined alpha, that was square root gamma 1. So this is the relation that you get. So now, so if assume that these things, these start at order epsilon, right? Then if this already started at order epsilon, then you won't get anything, right? If it starts at order epsilon square, which it turns out is the case here, that's the only way the epsilon piece cancels and you get the.
I would say it the other way around. This proves that gamma 1 starts with order epsilon square. Because you can take the root gamma 1 on the other side,
Yeah.
And you have these guys at order epsilon, you know that. Therefore, gamma has to be of order epsilon square. Is the proof?
Yeah, I guess maybe you can get your point. I think it will be about it. But anyway, this is a. So in particular, if you deal with CFTs in which this is not the case, then this won't work. Okay, so I'm finished basically, but just to make a technical aside. So Vassiliev and collaborators, they discussed the 2 plus epsilon dimensional Gross-Neveu model in a paper 2 decades back, and so it turns out that generally when you're doing this for fermions in the epsilon expansion, this is a generic feature. The fact that you get an infinite dimensional algebra of gamma matrices once you are in fractional dimensions, which means that so you can choose your spinors to be 2-dimensional in say 2 plus epsilon dimensions, but the gamma matrices. So when you take products of gamma matrices, you can use the Clifford algebra to generate a basis involving only antisymmetrized products. When you work in fractional dimensions, it turns out that the basis is infinite dimensional. That you can just keep considering higher and higher. So if you consider this, if you consider antisymmetrized gamma matrices, n of them. So what you can do is that you can, in a Gross-Neveu model, you can consider terms which are like this: so psi bar, gamma, and E psi, whole square. And now in 2 dimensions, of course, you only go up to n equal to 2 because it's finite dimensional basis, and the Sears identities tell you that all these things are related. Right? So for 0, 1, and 2, these are related, and so therefore you really only have just one term. Right? And now this is not the case once you are in fractional dimensions, and therefore you generate this whole tower of what are called evanescent operators. So if you work in d dimensions, then n less than d, you will get terms like these, and there will be various Sears identities between them. You can work with that. But for fractional dimensions, you get all these operators, and they're all independent. And therefore, when you're working in dimensional regularization, you generate all these things as counter terms. So notice that they are not like subleading terms. They are all the same order. And so you generate all these as counter terms, and therefore, to begin with, the kind of Lagrangian you should be working with should have all these things, all these infinitely many terms. So the assumption that we made implicitly was that you choose just V0, and then you hope that a renormalization will not generate these evanescent operators. So this is true only up to 2 loops. This is something that these people showed, which is a good thing. So we found this out after we had done the calculation. Luckily, it's something which shows up only at higher orders. So for example, if you consider 3-loop computation involving just V0, it turns out that V3 is generated, and so on and so forth. You can generate. So in general, you will have infinitely many force fermion interactions, and they'll all mix under renormalization. So it's a very complicated system. And these people in 2 papers actually analyzed this, and they concluded that some of the numerical computations in this are actually not valid beyond. People had computed to order epsilon, Q, epsilon, so some of those won't be valid. But in summary, for our case, everything is okay, and probably to next order and epsilon, it's also okay. But beyond that, you will have to start worrying about infinite dimensional algebras and all these components being generated. So it is some technical issue here that I was mentioning this. Okay,
Let's start with questions from. Are there any questions from ICTS or HRI? Maybe ICTS first. ICTS, can you hear me?
You're muted.
No, I just switched it on.
Oh, it's muted.
Oh, it's the other way around. Oh, sorry. Oh, the light is on means that it's mute. Okay. ICTS, can you hear me? Any questions for Amin?
Yes, yes, there is a question. Is it possible to apply relatively to some fix the point of conformality exactly matter deformation?
Yeah, you can't really hear it.
It is speaking to
Someone give it
Is it possible to apply a technique to that fix the point, or is it possible to apply to the conformality theory with exactly marginal operator?
with
Exactly marginal operators can be applied instead.
with exactly marginal operators.
Finding out gamma to arbitrary orders along marginal
Yeah, to arbitrary orders, I don't think, because this technique is only give you leading order certain dimensions. Yeah, I mean, I'm not sure. I'll have to check in particular cases. I mean, if the conditions are met, which I assume, which leading order n plus dimensions, you should be able to extract everything.
Yes, so he is assuming that the anomalous dimension will start from the external sphere. So this is not regarded. And I think okay. Okay, no more questions from here.
Okay, any question from ICTS?
No questions from our side.
Okay, thank you. Now questions from TIFR.
Yes. Why did you assume that why do you assume it's you've done something only of operators? That relation between operators, like derivative acting on B is some operator. That relation is valid across some order in epsilon.
That thing can be generally true. The point is that you don't know what the normalized operators in general. No, the multiplet as a Schmidt-Dyson equation, that is exactly true, always. But the point is that, the equation that you were using was this, that rho is, right? And this thing is something which is order epsilon plus epsilon squared and so on. And this thing is order 1 plus epsilon plus more singular pieces, right? So the only thing that you can work out here is the leading thing. These things cancel and you get a finite. It might be possible to, maybe there's a way of going beyond that. I think generally you'll have to do much more than this. Because clearly, you can't expect to find anomalous dimensions to arbitrary orders without using more features of the cosine functions. So this just used 2 and 3 point functions. So this particular thing will enable you to extract only the leading order piece. You can't, because you have to take that cell and go to 0. This thing cancel against this. The others would give you there will be a finite number here, a finite number here, which have to match plus order epsilon directions. That you go ahead epsilon.
As a matter of principle, if I have some interacting compound here, let's say I have some UVB thing here, and I have flown down to some IRC.
Yeah.
Okay. As a matter of principle, there is no epsilon or anything here. I just have some, value of G star, whatever, and that value is some scheme dependent value, because now I say that, well, there is a way of tagging the operator psi bar psi or P to here. Okay. and that was some. So of course, for anything greater than 2, that was an irrelevant operator here, and presumably it will remain an irrelevant operator here. So I just tag it all the way. And how do I define this? How do I define this operator P2P? I can say that it should go up there as side by side to P. That's one. That's one condition.
Yeah.
And then it should be a primary field here. That's another condition.
In the free theory, it's a primary field.
In IRCFT,
yeah.
it should be a primary field.
Yeah.
And now you say that with that definition, this del slash of V being V1 being equal to V3 will also happen.
Yeah.
With respect to some suitability definition of V1.
Yeah, I mean, it's of course true that the interacting theory can have more operators which in the free limit become trivial or just become 0. So
so that does not define V1 and V3.
Yeah, so those anomalous dimensions of those, for example, you cannot compute using this thing. So these are only operators which smoothly you can connect to the free case. And the assumption, this is really an assumption thing. So Rychkov and Tan also in the paper, they just is a series of assumptions that you assume that you have this Fisher face point, and then there is a one-to-one map between, not one-to-one, but so every free theory operator has a corresponding unique operator in the interacting theory to which it goes to. Of course, there can be other operators in this interacting theory which do not survive the free limit. And these, of course, you cannot say anything. That's also the reason that you cannot deal with isolated fixed points, because there is nothing you can break it.
Any further questions? Okay, so let's thank Amin again.